Hey, Dr. White back again, working with continuous type random variables. Want to look at expected value for continuous distributions and then some other topics about them. So how do you define the expected value for a continuous random variable x? Well, just like you did for discretes, you add up possible value times chance of that value over the sample space of all possible values. Except now it's continuous, so you're working with PDF instead of a PMF, so you're working with integrals instead of sums. But this integral from minus infinity to infinity is going to cover all the possible values for your random variable. And then here you are, each actual value, little x, times that product that I've got. And when you think about the kind of wrong but useful way of thinking about density functions, that's the height times the width of one of those skinny little rectangles that represents the probability of getting basically x. So same definition except in integral form. So let's go ahead and get the expected value for a uniform AB random variable. So we just try out the definition, and then we apply it. And for that, we got to be really careful thinking about what the probability density function actually is over all values of all real numbers. It's not 1 over b minus a. It's 0 for x is less than 1 over b minus a. It's 0 for x is, it's 0 for x is less than a. It's 0 for x is bigger than b. It's only the 1 over b minus a for the x's in between. And so that means that you don't have to do the integral from minus infinity to a. It's going to be 0. You don't have to do the integral from b to infinity. That's going to be 0. Area under 0 level curves is 0. You only need to do the integral for the stuff in between, the integral from a to b. So in this one step right here, we've actually divided the integral from minus infinity to infinity into 3 definite integrals: minus infinity to a to b, and b to infinity. And we have found in our minds that the first and the last of those definite integrals had to be 0. And so we're confronted only with the one in the middle. That kind of thinking goes on a lot when you are working with PDFs. Okay. Now we'll just use the fundamental theorem of calculus. We'll look at this. We'll get its antiderivative. There we are. And evaluate from a to b. And it comes out to be this. But don't leave it like that. B squared minus a squared factors as b minus a times b plus a. So there's a little bit of cancellation. And the resulting expression is much more illuminating. A plus b over 2 is the real number that's exactly halfway between a and b. And if you are picking real numbers between a and b at random equally likely to pick any one, on average, wouldn't you expect to get halfway between? So it works out. Just like with discrete random variables, there's special mathematical expectations for continuous random variables. So there's moments about the origin. There's moments about the mean. There's moment generating functions. It's the same thing. And so it's like the variance of capital X. So that's going to be the expected value of the second moment around the origin, that particular function of the random variable capital X. And so as an expectation, it is going to be the sum over the sample space of particular value times chance of getting that value. I'm going to go ahead and go for a formula, a quick shortcut formula for variance. So I'll go ahead and work this out generally rather than just heading to uniforms right now. So my plan is to square out little x minus mu squared. There it is, times the f of x dx. And then I'm going to apply properties of integrals. The integral of sums and differences is sums and differences of integrals. You want to know that from Calc 1. And we also know from Calc 1 that like if you've got a constant times a function of x, so like 2 mu is a constant times x, which is a function of x, then the integral of that would be, the constant, times the integral of the function of x. So to go from here to here, I'm actually employing a couple of different properties of integrals. And now let me see what I can do from there. So like, what does this work out to? I look at it and I see, oh, that's exactly the definition of the second moment around the origin, expected value of x squared. And this one here, well, that integral is exactly the definition of expected value of x, which I could write as mu. And so I've really got a minus 2 mu squared here. Now, how about this guy, the integral from minus infinity to infinity f of x dx? Well, I could follow this little arrow here. I could factor out the mu squared and just like focus in on that integral. So that's the total area underneath the F density curve. Now, areas under curves give chances for the random variable. So the total area underneath a density curve has got to be 1, just like the sum of all the probabilities in a probability mass function has to be 1. So this is really just mu squared times 1. That's the thinking I'm doing to connect this to say, well, Willie, it's just a mu squared. And then I just look at it, and I've only got a minus mu squared left out of this stuff. So I could write it as expected value of x squared minus expected value of x squared. So same shortcut formula as for discretes. So now if I want to take this to, the uniform distribution, my approach would be, let's just find the second moment around the origin first. And again, I don't have to go integral minus infinity to infinity because of all the places where little f is 0. I'll just focus in on the places where the little f is non-zero, and that's from a to b. And so I antiderivative, evaluate from a to b. I get this. Don't stop there, because there's actually a nice factoring pattern for the difference of cubes. If you don't believe me, take a piece of paper and multiply that out, and you'll get b cubed minus a cubed, and then commit it to memory because it is so useful. Anyway, there's a little more cancellation. Ta-da, there we are. And now for the variance, all I got to do is my expected of x squared minus my expected of x squared. So when I square out this, I'll have a 4 on the bottom, and I've got a 3 on the bottom here, so ouch. Common denominator would be a 12 when I stick those fractions together. And so, I fight, I do my algebra, and I, cancel out what I can. And in the miraculous way that things happen in kind of theoretical math situations, that turns out to be pretty simple. And in fact, it's just the square of a minus b, isn't it? Which I will write as b minus a squared, upper endpoint minus lower endpoint squared. So the variance of a uniform random variable is the square of the width of the interval it's based on over 12. So like the 12 doesn't strike me as anything particular. I'll just stop talking and go on. There are moment generating functions for continuous random variables. Let's go ahead and derive the MGF for uniform ABs. So moment generating function is a special mathematical expectation. It is the expected value of e to the capital X. That function of a random variable, e to the t capital X. Different one for every t. And so the expected value would be the sum over all possible values of little x, e to the t little x, times the chance that capital X would be little x. And so I just need to do this integral And so I kind of think about it. Oh, I have a typo. That should be going from A to B right there. That should be going from A to B. And the reason is that, like, I've already written in a 1 over B minus A here. That only happens for the x's between A and B. It's 0 otherwise. Sorry about that typo. Probably too lazy to fix it in the notes that you get. We'll see. So anyway, got to find the antiderivative of this stuff. So I just got a constant times this function of x. So I've got my constant times the antiderivative of that function of x. And if you think about it, this is really the antiderivative. Because if I took the derivative of this with respect to x, I'd have my 1 over t constant times the derivative of e to the tx, which is e to the tx times, says the chain rule, derivative of tx, which is the constant t, which would cancel the t on the bottom, leaving that as your derivative. So much thinking that goes on, when you see even detailed computations written down. There's a storm of thoughts that should go in your mind, or maybe be written out on a piece of scratch paper as you follow along to understand why things are as they are. That's the engagement that you need to really read mathematics. Okay, well, what we got? We evaluate from A to B, so we stick in the B, we stick in the A, we subtract, and we get all this stuff. That's the moment generating function for a uniform AB. Okay, let's play around with a couple of exercises. This is number 11. They just say, hey, here's a new random variable continuous type, and it's called capital Y. And I'm not going to quite tell you the density function, they say, but I'm going to call it little g of y. And we use a little y here as possible values for the random variable capital Y. Now, the support of this function is just the y's that are bigger than 1. It's going to be 0 everywhere else. Whenever they define a density function for you, and the stuff after the comma, that just says that this formula goes only for that stuff, and you are supposed to understand that the density function is 0 for all of the other real numbers. So like if you did a graph, it would be like this right skewed thing. 0 until the little y is a 1, and then it jumps up to be c over 1 cubed c after 1. Well, not exactly at 1, because they said y bigger than 1. So there's a little hole right here. And then you've got the c over y cubed graph, and so you've got this kind of a right skewed distribution or density function. Well, anyway, they didn't tell us c. Well, what is c if this is really the density function for a random variable? Well, to find it, that's where you use the areas under a density function give you chances. Total area under G would have to be 100%, because you've got to get something. So take that equation and work with it. 1 is the total area under the curve. You only need to go from 1 to infinity, because that's the support. C over y cubed, I'll write as c times y to the negative 3. Now, that's an improper integral. So I've got to set it up as the limit as some number n goes to infinity of the integral from 1 to n. Okay? C y to the negative 3 dy. And I guess I'll go ahead and take the antiderivative. And the antiderivative of y to a power is y to 1 bigger power over that 1 bigger power. So y to the minus 2 over minus 2. So that's like the power rule for antiderivatives. And the constant multiple still floating around outside. And I got to evaluate that between 1 and n. So I put in 1, and I subtract. And the minus here makes a plus, and I'll also factor out a c. So I've got this expression to take the limit of. And you can see as n goes bigger and bigger, that second fraction just gets closer to 0, so it is 0 in the limit, and all I'm left with is c over 2. Now we remember, like, why did we do all this? Oh, it was to find c. We know that 1 is c over 2, so we got a little equation, and we can solve it for c, and c happens to be 2. So now we really know the density function, and we can find out other stuff, like maybe what's the mean of y. So its expected value is the integral over its support of possible value times the probability of that value. So you got to do this improper integral. And I'm going to be a little bit sloppy and just kind of keep the infinities there rather than like setting up the formal limit. So I got my antiderivative, and I evaluate from 1 to infinity. So I stick in infinity and stick in 1 and I subtract. And I've definitely got a minus 2 over 1, which is 2. But then I think about, like, this is where, like, in my mind, I'm really doing the limits. What's minus 2 over bigger and bigger number? It's going to limit out to 0. And so I've got 2. So just accidentally, the expected value turns out to be 2, just like C did. It's a total accident. How about the variance? Let's see, what is the variance of this random variable? Well, I'll use the shortcut formula. So I'll go ahead and get the second moment around the origin first. And so I go over the entire support, y squared g of y dy. So I only have to go 1 to infinity, y squared, my 2 over y cubed dy. And so I simplify a little bit, and I got to do this definite integral, and I see 2 over y, and I say got to do its antiderivative, and that's 2 log y. So I got to evaluate that from 1 to infinity. So I plug in infinity, I plug in 1, I subtract, and log of 1 is 0. But what about the log of infinity? So really what's going on in your mind is log of n as n goes to infinity. And when you think about the graph of a logarithm function, it looks like this. For your point of view, it rises slowly, but it does go to infinity as the independent variable goes to infinity. So this is going to infinity. So expected value of y squared is this divergent improper integral. That means the variance is not going to be defined, which kind of, so this can happen to you. This little random variable has an expected value of 2. Now the variance is supposed to be the, a reasonable measure about how much the random variable could be expected to differ from its expected value. Well, the standard deviation, which is the square root, would be about how much you'd expect the random variable to differ from its mean. And the fact that it like diverges, that it goes to plus infinity, is kind of like saying that, wow, you could get big, super big variance away from the expected value. And that's because of this strong big tail off to the right. The more probability there is off to the infinite tail, the more likely it is that you might not get one of your higher moments. And in this case, we don't even get a second moment. Much less could we have other moments. When the second moment's not defined, the higher ones like third and fourth won't be either. So there is like no chance of a moment generating function here. There aren't even any moments past the first moment around the origin, the expected value. Here's another little exercise that's fun to consider, number 5. Suppose that y is a uniform 0, 1 random variable, okay? And consider the following new random variable w, which is a function of y. It's a plus b minus a times capital Y. So it's a linear function of y. A and b are constant real numbers. I only require that a be less than b. So like this linear function of y, what kind of random variable is it? What's its distribution? So to approach that, why don't we find the cumulative distribution function of w? So I'm looking for capital F of capital W at any possible value for capital W, little w, okay? So I'm looking for the probability that capital W is less than or equal to W. This is a really good thing to do. You got a new random variable that's a function of an old one. You want to find out about the new one? Use your knowledge of the old one, particularly through finding the cumulative distribution function. And here's why that's such a great idea. Well, the capital W is just the a plus b minus a times y. And so I just plug that in, and the event of capital W less than or equal to W is the event a plus b minus a capital Y less than or equal to W. I can take that algebra equation and solve it for capital Y. And I can find this probability because that expression is just asking for the chance that capital Y is less than or equal to a number. It's asking for a CDF value, and I know the CDF for uniforms. So I think for a little bit. My capital Y is a uniform 0, 1, okay? And so when I think about the CDF, I'm going to go back to the CDF for a uniform 0, 1. So let's see what we can do here. Tell you what, I'll just sort of head back way up to the CDF for a uniform 0, 1. And that's like way up. Here. So it's like, oh, page 2 of the notes. So this is the CDF for a uniform AB. And it had the value 0 if x was less than the left-hand endpoint, had the value 1 if x was bigger than the right-hand endpoint, and it had the x minus the left hand over the right hand minus left hand if x is between the left and right hands. So keeping that in mind, let's head back down and apply it, okay? Now, y is uniform 0, 1. So left-hand endpoint is a 0, right-hand endpoint is a 1. So I got to be 0 if the number they're asking about, w minus a over b minus a, is less than the left-hand endpoint. Got it. Now, in the middle, it's got to be my number minus my left-hand endpoint over right-hand minus left-hand if the number they're asking about is between the left hand and the right hand endpoints. I think that was supposed to be a less than or equal to right there. And then I got to be 1 if the number they're asking about is bigger. Oh, I'm sorry, no, this is right. It doesn't matter. It works out to be the same thing. Anyway, this is right. So I've got this complicated thing, and I just want to rework it a little bit. Now, the first bit, I just look at this and I multiply both sides by b minus a, and I'll still have like w minus a less than 0. So that first bit goes to this. Now, the second bit's awful, so let me just like procrastinate and do the third bit. So there, I take this and I multiply both sides by b minus a, and I get a b minus a on the left and a w minus a on the right. So I add an a to both sides and I get a b less than w. Okay, so this bit works to this bit. And no more procrastinating. I got to work with this bit. Okay. Well, this, when I think about it, actually just works down to this. But how about this? Well, I'll just pull that off, and like think about it for a longer time here. Here I am thinking. So here's my little inequality. And I think I really meant a less than sign here. Yeah. But I take all three sides of the inequality and I multiply by b minus a. So I still have a 0 here. I got just a w minus a here, and I got a 1 times b minus a here. I add an a to all three sides, and I get a less than w less than b. So I got here. So, looking pretty good. I'll look at this. I stare at it, and I realize, wait a minute. That's exactly the cumulative distribution function for a uniform AB. So our random variable, capital W, has to be a uniform AB all along. So it's kind of neat. It's not neat that I keep making the whole screen blue. It's kind of neat that this linear transformation of a uniform 0, 1 is a member of the same uniform family. It's just uniform on the interval AB. So you can get all other uniform random variables off of the uniform 0, 1 random variable. And you'll often find that's true for families of random variables. There'll be like one that you can easily get all the other members off of using some simple transformation. This isn't the last time we'll see that. Lastly, let's do exercise 17, a quote-unquote applied problem. So let's say that there's some insurance salesman and he's insured a business. He sold some insurance to some business. And let's let capital X be the losses that business is going to claim in the upcoming policy term, like say the upcoming year. Okay? So it's a random variable because it's a number that depends on chance. All kinds of chance factors, whether somebody breaks in and steals, whether or not there's like a fire, all that kind of stuff, determines the losses. And that's just, we just model that as chance. Let's define the loss ratio to be the losses this year divided by this constant, not a random variable, it's constant number t, which is the premium that the company charged the business. Okay. So this is the fraction of the premium that gets kind of that the company has to return to the business because they've insured the business. So the insurance company wants the loss ratio to be low. They would like their insurance salespeople to sell insurance to very unrisky businesses that don't claim a lot of X. Okay, and that way the insurance companies make a lot of profit. So to incentivize insurance salespeople to seek out and find and woo those safe businesses, you might give a bonus to insurance salespeople whose companies experience low loss ratios. So let's say that the insurance company has something set up like that, and there's a bonus they'll distribute to the salesperson. And here's the formula, okay? If the loss ratio is less than a half, then the size of the bonus shall be 1/2 minus the loss ratio times 1/30th of the premium. But if it goes any bigger than that, you get nothing. So you'll notice what's happening here, like the bigger the loss, the smaller 1/2 minus the loss is. Once the loss actually reaches 1/2, that product is a 0. And then they just like keep it at 0 for the loss ratios for any bigger than 50%. So you're only going to get a bonus if the company claims as losses less than or equal to less than 50% of what they were charging the premium. And the more they claim, the less you're going to get. And just to make things a little bit more fixed in the problem, they say, let's say that T is 300,000 bucks, and they're going to measure things in units of 100,000 bucks. So they say, let's say that T is 3. So we'll just use that once we go forward. And now, what's the distribution of the loss random variable? So again, measuring the loss random variable in 100,000 in units of 100,000 bucks. The density function they propose is 3 over x to the 4th, where the support is just bigger than 1. So actually, they're saying that for sure this company is going to claim more than $100,000 in losses, even though they were charged a premium of 300,000. So I guess even the safest business is still a bit risky. So given that that's the probabilities for the losses to be various values, what's the expected value of the bonus for the insurance salesperson? So to find the expected value, I would first rewrite the random variable a little bit. So like it's written up like this, but I'm going to multiply in the T over 30. And so I get a T over 60. And then I've got an LT over 30. But LT is actually X if you look back up there. So that's like an X over 30. Now that's supposed to hold if L is less than a half. Well, L is X over T, so it holds if X is less than half the premium T. And it's 0 if L is more than a half, which is equivalent to X is more than half the premium. Okay. Now let me go ahead and put in that T is the 300,000 bucks, T is 3, and so it comes out like this. If X is less than 3 over 2, and it comes 0 if X is more than 3 over 2. Okay, so it's actually pretty simple, the formula for the random variable B. So now we can get its expected value because it's a function of the random variable capital X. We just go over the possible values, the value that B has at each possible value of X, times the chance of getting that value of X. And so I only have to go, well, let's see here. What's the support of little f? Well, remember, it was just X is bigger than 1. So I know that little f will be 0 for all the x's less than 1, so I start at a 1. I also know that this b of x function here is going to be 0 once the losses go over 3/2. So I only have to take my integral up to 3/2. But in between those two values, the b of x is this, and the little f of x is this. And so I can multiply those in, and then I have this little definite integral that I got to find. And I could go work it out. And I don't care what it is, but if you're the insurance salesperson, you should work it out because then you know the expected value for your bonus. Cool. Last little topic is percentiles for continuous random variables. So let me define the concept of a percentile in general. The 100th percentile of a random variable x is a number that I shall write pi sub p, just a fixed number, which has the property that the integral from minus infinity to pi p of the density function is p. Now the integral from minus infinity to pi p of the density is the chance that the random variable is less than or equal to pi p. So what they're doing here is they're actually looking for a number. When you're looking for a percentile, you're looking for a number so that the chance of being less than that number is any fixed chance that you're interested in. For example, say you want the 70th percentile of a distribution. Imagine this picture of the density function. And there's the 70th percentile somewhere along the x-axis. And what has to happen is that 70% of the total area under the density curve has to come before that percentile. Okay? So this picture should be your guiding picture when you think about percentiles. Now there's some famous percentiles. The 50th percentile is called the median of a distribution. The 25th percentile is the first quartile of the distribution. There's a 1 in 4 chance that your random variable will come out less than the first quartile. And the third quartile of a distribution is the 75th percentile. There's a 3/4 chance of coming less than the third quartile, only a 1/4 chance of coming bigger than the third quartile. So computational example, say we've got some probability density function. And 3/2 x squared for x between -1 and 1. That really is a PDF. If you integrate it over the support, you do get a 1 for 100%. Find the median of this random variable that has, this f as a PDF. So looking at the graph, of little f, it is symmetric around 0. And so if I want the median, I want the number so that half the area is before that number. Well, the shaded area under the curve here has to be the shaded area under the curve here by the symmetry. So that median had better be 0. If I don't get that at the end of this computation, I know there's a mistake somewhere. But let me do the computation. So I set it up. P is the integral from -infinity to pi sub p, f of x dx. And I work with my support, I just go -1 to pi 0.5. 3/2 x squared dx. And so I do, let's see, the integral of 3x squared is exactly an x cubed. I've still got my over 2 hanging around. I evaluate at pi 0.5 and at -1. So I got pi 0.5 cubed over 2 minus a -1 cubed over 2, which simplifies to this stuff. And so I say that the half has to equal this stuff. So I set up this little equation that I can solve for the median. And so I do. And you take away half from both sides, and you see that pi 0.5 cubed over 2 would be 0. So pi 0.5 would have to be 0. The median is 0, like I promised. So that's our introduction to continuous random variables. Along the way, we met our first official family of continuous random variables, the uniform family. There is a way to compute with the uniform family in R. There's like D unif and P unif and R unif if you want random ones. Most people don't do computations with the uniform because the probabilities are so easy to find by hand. Random uniforms, they often do generate in R, so we'll probably use some R unifs in the future. But I'm going to defer any R work with uniforms until a later section. So that's it for now. See you another time.